And welcome to a new video about circuit design. This is our second example where we consider another design example. Of course, we'll look at our calculations step by step and also verify these in SPICE simulations. So let's look at our example. We have this following circuit given, electric circuit with two DC voltage sources VA and VB and three resistors R1, R2 and our load RL here between the nodes T and L. VA is 15 volts, VB is 20, and R1 is 60 ohms, R2 is 40 ohms, and load is 10 ohms. So everything is actually given. But the question here is the following. Under these conditions, only 75% of the required power is delivered to the load. So not 100%. We need 100%. And now the question is actually the following. Design this electric circuit by adjusting only the DC voltage sources. So we can only, let's say, change the values of the VA and VB such that the required power is delivered to the load and both sources contribute equal power. So we have actually two conditions. We need to have 100% of the required power, not 75%, that is one. And the second thing is we need that VA and VB deliver equal power. So they must contribute equally. So that's actually sort of a combined problem. So also a little bit challenging compared to example number one. So let's see what we need to do here. Okay, look at the solutions. First, let's write down specifically what the situation is. First situation is actually the current situation, what we have now. In this case, we have a load power, which is given by this expression, the load current and also a load current squared times load resistor, and that is 75% of the required power. So this is the original case. And this is the load current flowing here, and this is the load voltage assigned here as shown. Now we have a situation 2 that must be the new situation, and there we have a new load power must be equal to the new load current squared times load resistor, and that is the 100% of the required power. So this new condition is what we actually need to have. Okay, let's now look at this solutions step by step. First step is actually, in this case, I start with the mesh current analysis and I choose a loop direction to calculate the required the current and also other unknowns. So I make a loop for this case. I call it IX, so I go clockwise for this loop. I have also another loop here and I will call that IY. Now then I will write the loop equations, that is actually Kirchhoff voltage law for each part, so for each loop. So loop X, I can say minus VA, and then R1 plus R2 times IX, minus, because that is fighting back. We have discussed this also in great detail in the videos about mesh current analysis. So you see minus R2 times IY, and also plus VB, and then you make actually the full circle. So you start actually here, minus VA plus R1 times R1 plus R2 in parentheses times IX, and then minus R2 times IY, and then plus VB is equal to 0. Now we can now bring everything as a variable to the left side and the constant to the right side, so you will get this. So the VA and VB goes to the right, you get this expression. And if I now substitute the values, we have 60 ohms for R1, 40 ohms for R2, and 15 volts for VB. VA and VB is 20 ohms, 20 volts, so you get this expression. Now we can divide this by 5, and you will now have this expression 20 IX minus 8 IY is minus 1. Now let's call this equation number 1. We need it later. So now do this similar thing for loop Y. We go with minus VB, and then we see that IX is now fighting back because the current direction here in the second loop is actually also clockwise, but this is actually fighting back. So this is why we have minus R2 IX, and then we have R2 plus RL, these two resistors in series together, times IY must be equal to 0. Again, set the constant to the right hand side and keep the variables to the left. This is then the equation you get, and if I now substitute the values, I have this minus 40 IX plus 40 plus 10 in parentheses times IY is equal to 20. Now this is equal to this, and if I now divide by 10, I have this expression. So minus 4ix plus 5 times iy is equal to 2. And that is now our second equation. So we can now use this, solve the unknown loop currents, which is then ix and iy. But remember, we know that iy is equal to il. So this is actually our main objective, to calculate the iy. So let's bring these two equations here together, so on top of each other. And in order to eliminate one of the parameters, one of the variables, you need to make them equal to each other. So you can say I have here 20 times ix. Let's make this also 20 times ix. That is done by multiplying this second equation by 5. You can also say I want to have the minus this iy eliminated. Then you need to make this coefficient and this coefficient equal to each other. So you can choose by multiplying this by 5 and this by 8, and then you can work it out. I have chosen for multiplication of the second equation by 5 and keep this first equation as it is. Then I get the following. Why actually? Because I want the iy that is related to il, and that is the load current. So I keep the first equation as it is, and second equation I multiply by 5. So you get minus 20 ix plus 25 iy is equal to 10. Now I now add them up and then lose actually my ix, that's gone. This will be 17 times iy will be 9. So minus 1 plus 10 will be 9. So if I now work this out, it will be then 17 iy is equal to 9. So iy will be then 9 over 17, approximately 529.4 milliamps. Now, if I also calculate ix, I can do that using this expression or this expression. So you can use equation number 1 or 2. So you just substitute iy and then work out ix. Then you will get 161.8 milliamps. We don't need this actually. This is really what we need, because the load current now in this current situation, situation 1, is equal to iy, which is 529.4 milliamps. This is really the information we needed. Okay, let's move on and keep it also here, this information, for future calculations later. Now the load power for situation 1, current situation, was given by this expression. If I now calculate the actual load power now for this situation 1, the current situation, I can just use this formula and then substitute the value we have found for the current. So we have current squared times the resistor value, which is 10, and I get 2.803 watts. This is actually what we have, and this is actually 75% of the required power. So I need to go to the situation 2, which is the new situation. I need to make this 100%. And this is the equation. So I need to find actually a new current, because I cannot change the load resistor. I can only change VA and VB. That's actually given in the question in place here. So I can only change the current also. So the resistor stays the same. So that's still 10. So this must be 100% of the required load power. So what can I do? Let's make a table. This is situation 1. This is situation 2. Load power was given, already calculated here, 2.803 watts. This percentage of that is 75%. I need to go to the 100%. That means this is now unknown for the situation 1, situation 2. So how can I do that? Now you can see, in order to go from 75% to 100%, I can multiply by a scaling factor, which is 100 over 75. In order to do that, I also need to do the watt here. So this power also must be multiplied by 100 over 75. So the equation is actually given by this. So 100 over 75 times this power will be this new load power required, which is then given by 3.737 watts. This is now the 100% of the required power. All right. Now, thus the new load current must be using this formula. We have this formula. Now we can substitute everything we have. We can also write down the new load current in terms of the new load power divided by the load resistance. So this is I squared, of course, so you need to take the square root. Let's substitute everything we have. We have the 10 ohms and also the new power for the load. I get 611.3 milliamps. So this is now the new required load current. All right. Now the new load voltage, because since this is changing, the load voltage will also change. That is really calculated using Ohm's law or using this formula, because you can say P is equal to V times R. Now we have this. We know then the VL new, so the new load voltage will be then the new load power divided by the new load current. Now we have everything, so we can calculate that must be then 6.113 volts. You can also use Ohm's law because you know the resistor value. You also know the current, so you can just say current times the resistor value and you have also exact same result. So that is also possible. Okay, now we have actually our required information. New load current, new load voltage, and new load power. This is all for situation number 2, where we need 100% of the required power. Okay, let's now look at the power delivered by each source. So VA is given by this expression, so VA times IA, that is just the current delivered by the source VA. That's PA, and a similar form from VB is actually the similar equation, VB times IB. That's actually the current flowing out of this source here, going up. Okay, now both sources must contribute equal power, that's given. So that means PA must be equal to PB, because that must be equal to each other. So they need to contribute exactly equal power. So I can say, and we can say, Kirchhoff's current law at this node T. We can apply that by assigning these two currents. So I can make IA and IB now. These are the currents. And now we can say this new load current must be produced by IA and IB together, because we know this current is equal to IA plus IB. That is because these two come together in this node and then produces the new load current. Now we can now expand this equation, the Kirchhoff current law at node T, and write down the IA and IB in terms of voltages and resistors, because that will help us in order to calculate the rest of the parameters. VA we don't know, that is actually a new VA, so this VA of 15 volts I cannot use anymore, so that will be a new VA, and this new VB will be also calculated. So, and I have now minus VL new divided by R2, that is actually the voltage drop across R1. Divided by R1 will give you the current. And similar for the IB, the voltage across this resistor is this voltage minus the voltage across the load divided by then the resistor R2 will give the current, so that's actually shown here. And again, the VA and VB here are the new voltage values for these sources, not the current values of 15 and 20. So I cannot substitute that. So in order to go, I need to keep them as a variable, and then we have 0.6113 as our new load current. That is the left hand side, and the right hand side I can substitute the new load voltage and also the resistors and have this expression. Now let's multiply left and right hand side by 60. That will give us a little bit easier expression without any fraction, and this is what we have. And if I again work it out, 1.5 is VB and also 1.5 is minus 6.113, you will get this. Now let's bring everything together and then place here on the left hand side the constant, so I can move this and this part to the left hand side and keep the VA plus 1.5 VB to the right. And I have this. And I can now call this equation number 3, and we will use it later. Now, I need this. That means PA must equal to PB. I can say then, this equation VA times IA must be equal to VB times IB. That is what we have from this condition. Now, let's then write down this equation using also the expressions for IA in terms of the new VA and also in terms of the new VBs. Again, remember the VA and VBs here are all new values for the sources, not this 15 and 20 volts. So I cannot substitute them. Now I will now substitute the values we have found for the new load voltage and also the resistors R1 and R2 given here in the example. So this is what we have. Okay, we have 6.113 and 60 and 40 for the R1 and R2 respectively. And then we can now again multiply by 60 left hand side and right hand side, so we get rid of these fractions. 60 over 40 is again 1.5, so I get this expression. You can see we have still two unknowns, but we already had actually an expression with two unknowns. So we have now the fourth equation, and we now have equation number 3 and 4 together will be two equations and two unknowns, so we can solve it. Okay, of course this is a little bit complicated expression. We have actually here, let's say, a quadratic expression. So I need to now a little bit work it in a different way. So I need to say, rewrite now equation number 3 as follows. I can say VA is equal to 51.961 minus 1.5 VB. And call this equation number 5. And if I now substitute this equation number 5 in equation number 4, I get only variables, only the variable VB. So everything is actually gone, only VB is there. So that will be then this. So VA will be then this, so you get in parentheses this expression. This will be here will be then 51.961 minus 1.5 VB, and then still the second part in the parentheses. And this is still the same, so the right hand side is just exact same as equation number 4. Now I need to now use this. We can still simplify this further, so we can take this and this together, and that will give you 45.848, and the rest are exactly the same. Now we need to solve this. Now we can solve this. You can work out the parentheses, you get the quadratic equation. You can solve it using the formula for the quadratic equation, or you can use it in numerical solutions. So I will do that. So I will solve it in a numerical way. So I would like to solve it this using a graphing calculator, for example, or using a simulation program. So I have then a plot that will give us also a little bit more insight. This is the blue, this part of the equation. Right inside is this blue graph, you can see it. And this brown part is given by the brown color. And the x-axis actually our DC voltage source VB. That is the, let's say, the x-axis, our x value. And the value of this expression, or that expression, is this y value. You can see the intersection point, that is also what we require, is here. It is shown here and also given here in dashed red box. That is 19.365, and that is also the value for VB. So we read this value from the plot. And this doesn't mean anything, so we don't need this value, we only need this x value. Then we get the following. Since we know VB, we can calculate VA, because VA was given by this expression. So we know that VA can be calculated once you know VB. So we know VB, you substitute that 1.5 times the 19.365, and you put it in that equation, you get 22.914 volts. So we now have VA and also the VB. These are the new values for my voltage source. So I need to increase my voltage source VA from 15 to 22.914 volts. I also need to actually decrease VB from 20 volts to 19.365 volts. So these are the adjustments you need to make. Okay, let's move on. Again, these are the values we had for our load, current, voltage and power in the new case, in situation number 2. Now let's check the delivered power now for each DC voltage source, because we need to check that, because we have something determined already, but let's also check that. So we know this is the formula for the VA. This was the voltage we have determined, and the current can be calculated again using the IA formula. Again, the new value for our VA. If I now put it in, that will be then 22.914 minus that 6.113 over 60 will give me 280 milliamps. So 280.0 actually, more accurate, milliamps. That's now the current. So we know the current, we know the voltage. So I can say, let's then calculate the power by this source. That will be then multiplication of the VA and IA. I get 6.416 watts. So that is for PA. Now we need to calculate the similar thing for VB, and I need to get exact same, because they need to be exactly equal to each other, because they need to contribute equally. So let's check that. DC voltage source VB. PB is equal to VB times IB. VB was already calculated, and IB can be calculated in a similar form. So I can have this formula. Again, the voltage drop across this divided by its resistance. We have the value, new value for the VB. This is the new value for the load voltage divided by 40 for the R2, and I get 331.3 milliamps. That is the current will be flowing here in the new condition, and this is the 280.0 milliamps. If I now multiply VB times IB, this I get nicely the same value, so I get 6.416 watts. So PA is equal to PB, so we have checked that. That's good. Let's also check or calculate also the IL, because IL new was IA plus IB, and we have now the currents IA and IB here. So IA and IB, if I add them up according to this, that is due to the Kirchhoff current law, you get 0.6113 amps or 611.3 milliamps, which is what we have calculated. So that is also confirmed here. Perfect. Now let's move on. Let's see what we have in our simulations, because we have now done the required calculations. We have found the new VA and VBs. Let's also check that. This is the simulation diagram, the circuit actually I have drawn in the simulator. You can see the VA and the VB, the new values, R1 and R2 here, and also the load. I also placed the current meter here. There's a current arrow. This is a current meter for this branch, so IB. This is IA, and you can see also IL, which measures the current through the load. And also this meter node will measure the voltage between these node and ground. What you see is the following. We have a couple of values, but we have calculated these. So we see VL new, the load voltage new, was 6.113 volts, exactly the same in the simulator. The load new load current was 611.3 milliamps, very close to the value given in the simulator. The VA is this, and the current in that branch was 280.0 milliamps according to our calculations, and we see it is very close to that. And I see in this branch is 331.3 milliamps, also very close to that value. That's a very small difference, just rounding off errors, nothing to do with our, let's say, error in our calculations. And if I now use these two values multiplying together, you will get the power for the load, new load power, the power given by this VA, and the power given by this VB voltage source. Now you can also generate the table. You can actually see them here. So we have all the currents, IA, IB, and IL. So they are given in table form. That's also nice to see all of them, let's say, together. And we have also the voltages for the load and also for the resistors and the other parameters. So we can also see a lot of information in this table. But we have verified using the simulation that the calculated values, the new VA and the VB are correct, such that the power delivered by each source is equal, and now we have 100% of the required power instead of 75% of the required power. Alright guys, this is for this example. I will show you now the actual simulator, the circuit in the simulation, in the SPICE, and we will also see how you can generate these values there, and also how you can generate these table there also. So let's now jump to the simulator and then conclude this example. Alright, we are now here in the simulator. I already prepared the circuit for you. You can see the new value of the VA, new value for the VB. This is the resistor, this is the R1 and R2, and this is the load resistor. And you can see here the arrows for measuring the current. So IA will be measured using this current arrow, IB with this one, and IL with this one. This is the, let's say, the probe for measuring the voltage at some node. You can find this arrow here, so you can go to meters. So you can go to meter and you have an arrow here, current arrow. You can click on it and you get this one. So you can place it, and of course it must be placed in the direction where the current flows according to your choice. You can also get this, so by going to voltage pin, that is in order to measure, for example, the voltage here or voltage there. or voltage there in every node actually where you want it. So you can then change the name here. You can say, I want to make this V out, for example. That's also fine. So you can click on it and it will change. Okay, let's now do this. And we have now prepared the, let's say, the meters and the circuit. And I can now go to analysis and then DC analysis and then do calculate the node voltages. That means actually everything what is shown here as a meter will directly display its results. That's actually shown here. So you can see all the values we have also calculated and also shown in our discussion. You can also click on a component. It will be highlighted here in red. You can see the specific voltage and also the specific current for this element. So if I click on this one, you can also see the voltage and the current. But note that the current flows here from top to bottom. That's why it is the minus, so the opposite sign of this current value. It's also shown here. So it is just the choice of the simulator, of course. And again, you see minus 280 milliamps. And we have, of course, a plus because we go from this node to that node. Okay, you can also do a lot of other simulation results, but you can also generate the table. Let me also show you that. So how can you do that? Let me again repeat this. You go to analysis again, DC analysis, and then the table of DC results. Click on it. You get it. Now you get a lot of information. Now, again, you can click on a component and see highlighted in red the current and also the voltage. What you also see is 3.3,0 means actually between this node and that node. It's similar for this one. So you can check actually that you have this right component. You can also click on this, on that. You can see it will be highlighted for each of them. So the table is really nice to see. You have a lot of information. You can also see this IA, IB, and IL. So everything is here for the current. And also the voltage here for the VL is also shown. Alright guys, this is for this example, number 2, the design example of an electric circuit, where you have, let's say, not 100% of the power delivered to the source, and we have now managed by adjusting these two voltage sources, VA and VB, and now got here that 100% of the required power. If you have any questions about this exercise, please let me know and I will try to answer them as soon as possible. See you next time in another interesting video. Take care.